on to the next topic, let's have a review. Which element has the closest distance between its nucleus and its valence electrons? Another way of asking this is, which is the smallest element? So good if you said the smallest element was fluorine because it is most to the right and most to the top, therefore it is the smallest element. Now, knowing the size of the element will help you tremendously in thinking about electronegativity because they are very related. And electronegativity can be defined as the ability to attract shared electrons to itself. So if you think about the size and electronegativity, the smaller your atom is, the closer your nucleus is to that shared valence electron. So if your positive charge is closer to that shared electron, you will have a stronger attraction to it, so you will attract it much more to your side. Whereas if you are a large atom, your nucleus is very far away from that valence electrons. Your nucleus will have to go through many layers of negatively charged electrons before it even sees that last valence electron to attract it to itself. So because of that, fluorine is your most electronegative atom. It is your smallest atom. Now this is a table that gives you the electronegativity values and is empirically determined. It was measured in the laboratory. Another trend in electronegativity that you may notice is that nonmetals will tend to have higher electronegativity values, whereas metals will have very low electronegativity values. Remember that metals like to give away its electron, so therefore it doesn't have that strong of an attraction to the electrons in a bond. So what does this electronegativity have to do with anything? Looking back at the bond between hydrogen and hydrogen, since they are identical to each other, the electrons that they share between them are shared very equally. 50-50 you could say, because they are identical to each other. Imagine if there was a tug of war and there were two people with the same strength, and if they were pulling to get those electrons, neither of them will have the electrons more to its side. So we say that there are equal sharing of electrons, and we call this bond not only covalent bond, but it is a non-polar covalent bond. Whereas on the right-hand side, the bond between hydrogen and chlorine, that's categorized as an unequal sharing of electrons. So that covalent bond is called a polar covalent bond. Again, you can go back to the previous slide to see that chlorine has a greater electronegativity value than hydrogen, so it can pull electrons to itself better. To annotate that electrons aren't shared equally in this bond, we can put a sign that is a Greek letter delta, meaning partial, and negative, meaning that this chlorine is partially negative, whereas this hydrogen has a delta positive, meaning partially positive, and hydrogen has a partially positive charge on itself because electrons are being pulled this way. With this layer of electronegativity to understand bonding, let's add another definition to ionic bonds that we covered in last lecture. Remember that we said that ionic bond occurs between a metal and a non-metal and is a result of electron transfer. And in terms of electronegativity, it also has a large electronegativity difference of 1.8 or more. So if you take the difference between two atoms' electronegativity values, if it is greater than 1.8, then it is an ionic bond. So for example, if you take a look back at that chart, the difference in electronegativity between chlorine and potassium is 2.2. And the difference is always going to be an absolute value. You just take the larger value, subtract it from the lesser value. Let's do some more examples. You have nitrogen and sodium. What would its electronegativity difference be? 2.1. What about sulfur and cesium? 1.8. You can see that all of these are greater than 1.8 and that they are difference between a metal and a non-metal. Both of these definitions will fit ionic bond. But again, I said there are two types of covalent bond, polar and non-polar. So let's talk about the polar one first. From that first slide, we saw HCl bonding. And if you take their difference in electronegativity, delta En, you will see that it's 0.9. It's less than 1.8. What about carbon and oxygen, another two nonmetals? It's 1.0. What about nitrogen and oxygen? 0.5. So it turns out if you have an electronegativity difference of 0.5 to 1.8, you are considered polar covalent bond. So from the previous slide, we saw that ionic bonds result from an atom pulling electrons totally to itself, where the difference of electronegativity is greater than 1.8. So if it pulls electrons to itself so successfully, you can imagine that one side is a full negative charge and one side is a full positive charge. Comparing that to a polar covalent bond, we know that the electrons are still being shared and not pulled completely to one side. We can again call that being partially negative on one side and partially positive on the other side. So in this kind of drawing here, we can see that most of the electron, which is purple, is on one side, but still this side is not completely devoid of that purple electron shading. Contrast that to a nonpolar covalent bond. In a nonpolar covalent bond, your electronegativity difference will be 0.4 or less. So for example, if you are a bond between identical atoms, nitrogen and nitrogen in this case, you will have 0 as your electronegativity difference. Even if you are different elements, you can also still be nonpolar if your electronegativity difference is equal to or less than 0.4. So for example, in this case, the difference in electronegativity of hydrogen and carbon is 0.4, so it is still considered a nonpolar covalent bond. So you can depict that with electron density being shared equally among the two atoms. Let's summarize it. If your difference is between 0 and 0.4, you are considered nonpolar. And if your difference is between 0.4 and 1.8, you are polar. And if your difference is greater than 1.8, you are ionic. Now actually, I don't like to use this chart very much because I like for students to have a more fluid understanding. So I want you to be able to predict whether something is polar, nonpolar, or ionic just based on the periodic table itself. And to help you do that, you should memorize this fact that carbon and hydrogen is always going to be nonpolar. Remember, because their difference in electronegativity is 0.4. Anything other than that, you can use logic to reason. For example, if I give you two elements and one is a metal and one is a nonmetal, you will automatically say that's going to be ionic. You don't have to calculate delta En to know that fact. Or if I give you two elements that are nonmetal, like say oxygen and fluorine, you do not have to know the electronegativity values to tell me that's going to be a polar bond. You just know that fluorine is going to be more electronegative than oxygen because electronegativity increased from left to right. Same thing, if I give you oxygen and sulfur, you know that oxygen is more electronegative than sulfur, so you can draw a bond where oxygen will be partially negative. Now there are trickier cases where you would need the electronegativity value, but again, in this class I won't ask you those cases, and if I do, you can always answer it using the trends in electronegativity instead of electronegativity values when electronegativity values are not explicitly given to you. And when you have a polar covalent bond, you can depict that with a dipole arrow. A dipole is a separation of charges in a polar bond. You can think of dipole as just like the positive and negative side of a magnet. So for example, the bond between carbon and oxygen, you can designate again that oxygen is a little bit more electronegative, so it is partially negative, delta negative, whereas carbon is partially positive, that delta sign with the positive sign on top of it. You can draw a dipole, and a dipole sign always points to the more electronegative end, and that end has an arrow, whereas the opposite end will have something that resembles a positive sign. Let's see some more of these examples. Oxygen is more electronegative than nitrogen, so oxygen will be partially negative, so the dipole can be drawn towards the oxygen side. It doesn't matter where you draw this dipole sign, but most of the time you will see me drawing it on top of the bond. You can also draw dipoles in molecules. And when you draw dipoles in molecule, you want to draw it for each bond. So for in this case, hydrogen and carbon has no dipole because their electronegativity difference is 0.4, so it is nonpolar. Whereas carbon and nitrogen will be more electronegative than carbon. So we would draw a dipole towards nitrogen. Yay, checkpoint! Without looking up the electronegativity values, which of the following bond is considered a polar covalent bond? So let's do process of elimination. You want polar covalent. Polar covalent means that they have a large enough difference in electronegativity values. So you can cancel out sodium and fluorine because one's a metal, one is a nonmetal, so that's actually ionic. So now we have carbon, fluorine, carbon, 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 hydrogen. You can now cancel out C because carbon and carbon are identical to each other. And then lastly, you can cancel out D. Carbon and hydrogen have an electronegativity of 0.4, so that's going to be nonpolar covalent. So your last answer is going to be B, CF. So I will see you in class for more practice.